of the Civil Department. First of all, welcome to our seminar series. Actually, it's our celebrity seminar series. We had Professor Madanat from UC Berkeley last week. Now we're having Professor Linda Boyle from the University of Washington at Seattle. Our seminar series is organized by the Transportation Group of the Department of Civil Structural and Environmental Engineering, the Institute of Sustainable Transportation and Logistics, and from the TransInfo University Transportation Center. It is my great pleasure and with great excitement that I'm introducing Professor Linda Boyle. Professor Boyle is a professor and chair of the Department of Industrial Systems Engineering at the University of Washington at Seattle, and she also holds a joint appointment with the Department of Civil and Environmental Engineering. She's associate editor of the Accident Analysis and Prevention Journal. This is possibly one of the best journals in traffic safety, and possibly the next editor-in-chief.
Wow.
Well said. She's also the chair of the Statistics Committee of the Transportation Research Board of the National Academies, and and a very interesting aspect in her CV, if you had a chance to look at it, is that she has received over $19 million in research grants. So she's a multi-millionaire from the research perspective. And she has received grants from many agencies, including the National Science Foundation, where she received also the NSF Career Award. She has received funding from the National Institutes of Health, from several US DOTs, the DOT, from the Iowa DOT, Washington DOT. She has received even funding from Toyota, nearly $1 million of funding. Very interesting research. She has graduated several PhD graduates, PhD students. Many of them are holding positions in top institutions, not just in the US, but around the world as well. And has published extensively, nearly 150 papers, conference papers, technical reports, and so on, in top-tier journals, including Accident Analysis and Prevention, Transportation Research, Part C, Part F, in the areas of traffic safety, human factors in engineering, and general and statistical and econometric methodologies. Linda, thank you very much for being here with us today. With this, the floor is yours.
Okay.
Thank you very much.
Thank you very much for having me. I'm actually very excited to be back in Buffalo. For those of you who didn't hear what I was saying earlier, I graduated in 1986 and I haven't been back since, so it's been a real treat. This place has changed quite a bit since I've been here. I'm going to talk about some of the work that sort of culminates over several years of what I've been doing, looking at different types of data collection and analysis, specifically to look at road safety. So what is our goal, like when we look at road user safety? So our overall goal as researchers is to try to figure out how we can get the road user to their destination without any injury or undue harm. So when we look at safety research, we look at it from many different perspectives. We look at it from designing systems, services, and policies that can help enhance the overall health and well-being and safety of all the road users. And when we do that, we're looking at different types of tools and methodologies to identify what the factors are that can actually reduce the risks and enhance safety, across everybody in the transportation network. So when we think about the car of the future, it's actually very different from what our parents used to drive, or our grandparents, or even, maybe some of the older people. Technology is just changing the nature of driving. It's not just getting in your car and just going from one place to the next. There's many integrated features. Technology is a very big part. And there's a lot of stuff that is driving related as well as non-driving related. So these are just some pictures of things that is going on across the US. There's actually a large US DOT connected vehicle project that's going on based on the University of Michigan, looking at like the relationship between different cars and the sensors across from them. However, there's also a lot of systems that we're having in a car, like navigation systems, as well as using Siri, using the phone. I mean, how many of you actually use your phone while driving? Don't lie. Okay, how about if I ask the question a different way? How many of you have seen other people using their cell phones while driving? Yeah, everybody. How is that possible? How is it possible that everybody else is using their cell phone, but not me? So it's just kind of interesting in terms of like what we look at. So when we think about injuries and fatalities, why is it that it occurs? So I look at it from a human factors perspective. So I look at the human or the individual and how that person interacts with the environment as well as the vehicle and other things going on. So when I think about the road user and I think about all this technology that's coming in, I have to understand if we provide a service or a system or something to a person, to any individual on the road, what is it that they're going to do with it and how are they going to use it? But the problem is that they may not actually use it the way we would expect, henceforth why injuries, accidents, crashes may occur. The road user may not actually understand what the situation is. You know, they may not actually, if they're given information like on a variable message sign or a dynamic message sign, you know, those things that you see on the road, they may not actually accept the information that they see. If they see that there's a snowstorm ahead, they're like, well, I don't know, I don't really see any snow, I think I'm okay. They're just gonna keep going the way that they expect to do. Now, if they're given information in their car, like those of us who have navigation system, it says, turn right on Sheridan Road. It's like, I don't want to turn right on Sheridan Road. So you may not actually trust the information that you're given. And then you may not be willing to use it even if you do believe it's true. And then overall, it could be that you're given all this information, you may understand it, you may accept it, you may trust it, but you may not have enough time to actually make the appropriate decision. So these are all things to kind of consider when we're looking at road user safety. So how do we actually develop solutions? We want to be able to set up studies so that we can examine what these individual differences are. And there are many different types of individual differences. It could be because, you know, teen drivers are just different from older drivers. It could be that some individuals have different types of medical and cognitive impairments. They could be visually impaired, physically impaired. They could also be just really tired when they're driving. They've been driving for 12 hours and they're trying to figure out, like, you know, should they go on for like another half an hour more? They could be distracted, like we were talking about using your cell phone. They could be inattentive because of it. And there are some drivers that actually have a higher propensity to take risks compared to others. So when we're looking at evaluating different types of potential crash countermeasures, we have to take into account there are different ways to be able to look at it. So you may want to look at what their performance is at a specific snapshot in time. So in a particular place and time, they may be driving at a certain speed and driving in a certain lane in a certain way. So that's driving performance. But however, that performance, that speed that they're going at may actually change over time, and they may do it due to different situations. So when we look at evaluating what are different types of crash countermeasures, we don't only want to know what they're going to do at a particular situation, but what their behavior is and how that actually translates to like different situations. So we look at driver performance as well as driver behavior, what they're doing in a particular time frame, and then what they might do over longer periods of time. So when we think about how people adapt to behavior, and we're thinking about how we actually design systems, we think of it in terms of like, what we want to do as researchers is to make sure that we enhance their performance. So if we give a system, you know, if their performance is low, we're hoping that if they're given a system, like for example, a collision warning system or some information on the road, we're hoping that they would have an immediate positive response to it, that they will actually get better. And then over the short term, we actually might still see some increase in terms of like the performance. However, there's just so much that you can actually increase. So over the long term, you start kind of having this, you know, leveling off effect. As a matter of fact, you may not actually perform at some optimum level, and that you might actually just sort of fluctuate. Now, if this system was actually taken away, would a person actually drive the same way? Will they actually learn from their behavior, from using this particular system, whatever it may be? And you actually hope that they do. And if they do, that's considered a positive transfer. So they're given basically a system to use, and they use it over time, and they start learning how to actually drive perhaps a little bit better. So even if the system is gone, like let's say they go from their car to a rental car, which no longer has a particular feature, they kind of learn from that, and then they would have a positive transfer. Now, of course, that doesn't always happen. What might be actually more likely is that if the system is no longer there, it's deactivated, or you get into another car, you may actually go back to whatever your previous behavior is. If you go back to your previous behavior, then you're more in a neutral mode. So you don't have a positive transfer, but you actually just go back to whatever your previous behavior is. Now, of course, the other situation that can happen is you have become so accustomed to having that system there. Like, let's think about a navigation system, that if you go into a car with no navigation system, you're like, oh my gosh, what do I do now that I'm on Sheridan Road? Like all of a sudden you just become so used to having a system there that you actually have a negative transfer. In other words, your performance actually goes down. So when we look at these different types of behaviors, and there's different kind of continuums along them, we want to be able to figure out how do we actually quantify that type of behavior. So there are different ways that you can actually collect data. And it's along a different types of spectrum where you can have very, very controlled laboratory studies where we're, like if you think about like, those of you who've taken like intro to psychology where you participate in studies where you just look at like a stimulus response kind of thing. But at the same time, that provides you some information, but it may not be as realistic, in the real world. So you have things from very controlled laboratory studies all the way to like looking at just video data, on the road or looking at crash records. So this continuum actually provides some information where as you get further and further along toward this side, then you're getting more information about the real world. The unfortunate thing is that as you're getting more information about the real world, you have less experimental control. So as you have less experimental control, you may not be able to get as much insight about causality, like what is actually causing these crashes to occur. You can actually see these associations, but you may not be able to see them, as well in terms of like what happens if you make this change. So what I do as part of the research that I look at is I look at actually this whole spectrum of data collection tools and how I can actually use each one of them to actually get some insights on what that overall complete picture is of what that driver is. So I'll go through an example looking at something that's very popular right now in transportation research, which is naturalistic data. So there's actually right now a big study going on with 3,000 vehicles instrumented across the US where they're collecting data on everything to do with the driver. So this is a naturalistic driver where they have video data, they have sensors on the brakes, the accelerator, the steering wheel, so that we can get kind of like some insights as to what they're doing in different situations. So naturalistic studies are really nice because they provide insights into driver behavior for many different types of environments. And they can help identify the context associated with why a safety critical event may occur. Some things that we may not have even noticed before. The other thing is because crashes for a particular type of situation is actually considered very rare. What we want to do is be able to get some insights on what we can use to predict why a crash would occur. So looking at naturalistic data actually gives us some insights on the validity of different types of crash surrogate measures. And you can also capture these driver-initiated activities at any potential, situation. So we typically have for naturalistic data, things like video data, all these different cameras in the car that looks at you, looks away from you, looks at different sides of the roads. And then it might also even give you information about like different feedback during certain situations. So when I look at naturalistic data, I'm actually able to get what's called the initiating factors. So in other words, for a particular risk at a particular situation, I can actually see what that direct, intermediate, or immediate situation is. So I'm looking at the actual risk as they are basically interacting with the system as well as the environment. However, that again only gives me like one part of the picture. So one thing that I might want to do is be able to supplement it with some of the data from long-term exposure. So understanding like in a particular situation, if this is the risk that they have, if they're going to respond a certain way, what was the motivation associated with the driving? What were their attitudes, biases, as well as their experience with that road? And then, of course, there are limitations associated with human beings in general. We can just do so much when we're driving. So there is the actual risks and the perceived risks. And we can look at the combination of the two to find out why the driver would respond a certain way. And this is what's really nice about naturalistic data, is that you can get some of this insight in combination with other things. So I'm going to look at this. Yes, of course.
So for the naturalistic data, is it really control data or?
It's not control data. It's
just put the cameras and all the things.
Right, it's observational. There is some little bit of level of control depending on which studies that you do. So for example, in my lab, we actually have one car that's instrumented, and we actually have them do like, let's say, a set route. So we can control for things like that. But in terms of the weather, we can try to control what time of day so that we have less traffic congestion. But for the most part, you can't like control what, what's going to happen with other people, if there's pedestrians on the road, etc. So there is minimal control, I should say.
So for the naturalistic data, is it
for the 3,000 car naturalistic data? So the 3,000 car that's going on right now, and part of it is actually available online through the Department of Transportation, and I can talk to you about that later. So what they have is what I mean by minimal control is they have only certain types of vehicles that they actually instrumented. So if you have a car that's like 1990 or even 2000 and older, you're not gonna be part of the study because we needed to make sure that you had certain things as part of your onboard diagnostic system. So that would be an example. Also, we wanted to capture people from different age groups. So there was like 10 different age groups. And also we wanted to make sure we have males and females. So we basically made sure that it was separated out in different ways. And I know that Buffalo is one of the test sites as well for data collection. And Seattle was as well. So we can do some comparison studies, you guys. That would be cool. Going back to so the University of Michigan, by the way, actually collects a lot of field operational tests when they do studies. So that's pretty cool. So what I did was actually look at some of the naturalistic data associated with it. And I did this looking at a system called adaptive cruise control. How many of you know what adaptive cruise control is? Okay, what is adaptive? It's not conventional cruise control, adaptive cruise control.
Maintains a following distance
Maintains a following distance.
and varies your speed to keep the same distance?
Right, so what it does is if you know what conventional cruise control is, let's say you set it to 100 miles per hour, right? And you can just go at 100 miles per hour. If a car cuts in front of you, it will actually slow you down, right? And then once that car is no longer there, it will speed back up to whatever you set it at. And you can actually set the distance that you want it to trigger for it to slow down. So this is a system that has actually been in the US, it's been available since 2001, so for over a decade. Many studies have actually shown that it can enhance traffic flow as well as driver comfort. The problem is that the safety benefits associated with the system is actually very unclear. Even though people say that they might feel safer with it, there's really not as much comprehensive data. And the one thing that's really problematic is that this system is not 100% accurate in all situations. Actually, even today, in 2014, very few systems are actually able to operate in the following manner. ACC does not actually work in stop-and-go traffic. It doesn't work on curved roads because it's based on a radar system. So if you think about the field of view, if the curve is too short, you're not going to be able to detect that car. And then when there's a stopped vehicle, it actually doesn't detect what that stopped vehicle is. That's kind of henceforth why it doesn't actually work very well in stop-and-go traffic. So if you look at the user manual, it actually tells you not to operate it when it's under 25 miles per hour. And the reason why is because the system is based on two moving vehicles. So you're looking at what the algorithm is, and if it cannot detect another moving object, it assumes that it's not there. So it's basically looking at that. So we actually did surveys in Washington State as well as in Iowa, where I used to work at the University of Iowa, to basically try to understand whether or not people were really knowledgeable about what ACC can do. So we asked a question about, can ACC actually help you? So these were people that owned an ACC and have had it for several years. Does it work in stop-and-go traffic on curvy roads and for stopped vehicles? Now the right answer is no. But as you can see, there was quite a few people that said yes and don't know. As a matter of fact, over 50% of people who have ACC is not aware of what the limitations are associated with this system. So this is problematic because a lot of us are actually driving around with these particular vehicles. So this is where naturalistic data is actually really nice. So you can take a look at the field data and take a look at what the trajectory is of a particular individual and try to see where they are in terms of where they might be low risk in terms of that a car is really far away from them, when they start getting closer, so there's a lower risk, and then when they might actually be about to hit another vehicle. So what's nice about naturalistic data is that you can actually plot out what these trajectories are, and see what types of situations that they could be, and look at these different types of closing events. And you can actually break it out even more by looking at different situations, like what is considered a conflict, that there could be a potential problem, and when they could actually be in a near crash situation. So the difference is, when you look at this, you can also see how long that situation will be. You can see exactly when the adaptive cruise control would actually kick in. And then you can also see, right after it kicks in, if the driver was to intervene or respond, when they actually would respond. Now remember, the ACC system doesn't typically work in 3 different types of situations. So if the driver doesn't respond appropriately, you could actually be in a near crash or even a crash situation. So you can see for the near crash situation, it actually takes longer for a driver to respond. And the ACC basically needs to be able to, respond appropriately, but they may not be able to in a certain situation. So when we look at actually the distributions of all these different types of trajectories, we can look at their response time, and we can see that, so in the black lines, that's where the near crash events occurs, and you can actually see a differences in the distribution between those where the ACC and the driver intervenes and when the ACC is. So you can see the ACC actually takes a little bit longer. So if the car in front is too close, it actually might hit it. So that's kind of a problem that we wanted to look at a little bit further. So what's nice about this data, though, is that we have 66 participants, so this was a field operational test, where we had males and females in 3 different age groups. So we had them separated out that way from younger and middle-aged and older. And then we did a logistic regression model with a repeated measures design. And the reason why we use repeated measures is because we have 66 participants, but there's many types of closing events associated with them. So we wanted to be able to take a look at what the differences are. And we noticed in out of these almost 4,000 cases, about 459 drivers actually intervene in certain situations. So we wanted to see what was the likelihood that a driver would actually intervene given different situations. So when we did this logistic regression model, you can see this is just sort of like looking at the odds ratios. But here in this one, if you look at middle-aged drivers, because they're over this line, middle-aged drivers were more likely to intervene compared to younger drivers, for example. And then on this case, so the speed is actually on this side of the line. So if they actually drove lower speeds, they were less likely to intervene. And if they were on the highway, they were less likely to intervene as well. So now that we have kind of like a little bit of a profile from the naturalistic data, we want to be able to see how does that translate to looking at drivers in terms of their risks. So when we think about the naturalistic data, we can't actually establish causality. We can only look at what these relationships are and try to understand, well, what is the likelihood that a driver might intervene in one situation compared to another? The challenges associated with naturalistic data is I'm trying to parse out all these differences. It can be challenging because all of this was done, on the road for different types of conditions in different types of situations, and everybody's in, something different. So the measurements also may not actually be as good. There's a lot of noise when we're collecting data on the road. So, it could be due to adverse weather conditions. All those video data, I can't always see what the driver's looking at. They might be wearing sunglasses, there might be glare, there may be a lot of things that's just really hard to see. Also, when I'm looking at one factor, that one factor can actually be a multitude of a lot of different factors. So that variable of interest may actually consist of many different things. The other thing about naturalistic data is that it's very difficult to have the same sample sizes across each of these conditions. They're actually going to be incredibly varied. So how do we take that into account? So as an example, like what the challenges are, so I can use driver distraction as an example. So this is a really big topic these days, and the impact of driver distraction on crash risk can be dependent on many different things. So in the real world, when we're looking at naturalistic data, we actually see that driver distraction can be impacted by the type of distraction. So if you're using a cell phone, compared like talking to your child in the back compared to eating or talking to a passenger, that is different. And so you have to be able to look at what those differences are. Even if I am just looking at a cell phone, there's different types of cell phones, right? The Droid works very differently from the iPhone, which works very differently from the BlackBerry. And my interactions with them would be very different. Also, where do you have your phone? Is it basically mounted in the middle? Is it in my purse? Is it in my back pocket? Is it sitting on my lap? So you have to be able to say, well, if I understand that, that actually may impact the likelihood of being involved in some sort of a safety critical event. Same thing with the type of interaction. Am I dialing? Am I calling? Am I just looking at it for whatever? So all of those things, all these different circumstances can have an impact on driver distraction. And why this is an important issue is because there's actually been a lot of studies right now that say, well, maybe cell phones is a protective effect. But what do we mean by that? So if we look at something simple like just dialing with your cell phone, just basically plugging in a number, you might look at, for example, the brake reaction time. And you're like, that's weird. I've noticed that the brake reaction time is pretty quick when I'm doing a cell phone dialing. Or is it really? So let's say I collect data on 1,300 observations. And now for 1,300 observations, I see that there's actually 3 different types of dialing that I can do. I could be doing touchscreen dialing, handheld voice dialing, or Bluetooth dialing. So in many states, using a handheld or doing touching, screen is actually illegal. So you would not expect to see as many of those types of situations compared to Bluetooth dialing. But yet Bluetooth dialing, because there's more of these observations, is actually pulling the distribution toward one side. But if I was to parse this out, I might actually see a different picture in terms of like the break reaction time, and we might actually be slower than we expect. As a matter of fact, if I was to look at these two, the touchscreen dialing and Bluetooth dialing, so this is what touchscreen dialing would be and Bluetooth dialing, we may actually find an even different story, which is that in these 150 observations, there's only 75 participants. In other words, there's about like 1 to 3 observations per person. Okay, so only about half of the sample is unique. Well, but in Bluetooth dialing, which is more likely, it could be that there's only 90 participants. So it's like 5 to 15 observations per person. So even though there's 900 observations, it's only 1/10 of the sample is unique. So that has to be taken into account when you're looking at what these differences are. So you also need to look at not just what that one factor is, what are the relationships across them, and then how many different observations, unique observations are there. And I'll talk a little bit more about that in a little bit. So going back to this figure, where I'm looking at the naturalistic data as well as looking at some survey data about long-term exposure, if I was to connect that to try to get some information about the driver, I can establish this relationship. But if I want to know how I actually mitigate these effects, I need something to be able to close this loop so that I can take a look at these responses, figure out what information can I provide that can actually perhaps might change what their perception is of the actual and the perceived risk that can actually impact their safety outcome. And this is where actually driving simulator data could actually be very valuable. You can actually get some more control data to take a look at it. So going back to this spectrum of data collection, if we go to the other end of the spectrum, which is a little bit more controlled, the driving simulator data, we may be able to get some different information. So the nice thing about driving simulator data is I can take like a specific scenario and repeat it over and over again. And I could do that with somewhat equal sample sizes if I plan it correctly. And I can also examine different types of potential road and vehicle improvements before I spend millions of dollars putting it on the road. And I can use it to help guide what I should be doing for all these different types of vehicle systems. So you can use driving simulator data to be able to look at all these different things. So going back to the adaptive cruise control study, we wanted to be able to examine different patterns of behavior associated with adaptive cruise control. So we used a University of Iowa motion-based simulator. So for those of you who do not know, the NADS, which stands for National Advanced Driving Simulator, is actually the largest research simulator in the world. There's actually larger simulators that are more for like other things like for Toyota or for training, but this one is actually the largest in terms of research. And so what we did was we actually replaced the vehicle cab with one that had a Toyota setting, because Toyota Lexus actually creates an adaptive cruise control system that is widely used. So we actually did that survey that we did earlier. We actually found out that over 50% of the people who actually use ACC and own it actually own a Toyota Lexus type of car. And the reason why I say Toyota Lexus, for those of you who do not know, that Toyota and Lexus are the same company, so they actually use the same type of system. And so we basically set it up so that they actually use the ACC the same way as what they do in Toyota. And this is actually what they see on the screen. It's kind of dark, but what happens is when you get very close to a vehicle, there's actually a little light that shines up, and it shows you how close you are or how far you are from that system. And what users can do is they can set either a short, medium, or a long headway in terms of how far you want to be from the car. So what we did was we collected 24 data points from experienced people who have actually used Toyota or a Lexus. And the data that we collected, the mean age at the time was 56.7. Most of the people who own these cars, because they were more of the higher end cars, tend to be older. So it's something to kind of think about when you're analyzing your data. So what we did was we did a cluster analysis, and a cluster analysis, for those of you who do not know, is basically used to group people based on different types of variables that you feel might provide some information about the likeness. So we grouped them based on 4 different variables, looking at the number of times that the driver would actually disengage ACC by pressing on the brake, the number of ACC warnings that they got issued before they did something, the percent that actually set it at short, medium, and long. So you can actually change the setting even as you're driving. And then what the differences were between what they set as the speed and what the posted speed was. So we use these 4 variables to kind of get like a picture of what these drivers are like. So when we did that, we actually color-coded it so that we had like people that were more conservative to more risky. So if they tend to disengage the ACC more often, they were like, they felt that they wanted to take over more. They were more conservative. And then we have people that like allowed the system to have like tons of warning, like over 3 compared to like very, very small. And then there were some people that would set their cruise control speed at higher than the posted speed. So we kind of used this to get like an assessment of what these drivers were. And so from this thing, we actually grouped them into 3 clusters. One which we called the conservative drivers. The second one was moderately risky, and then the third one was like the risky drivers. So we looked at this in the context of, well, why is it that some people are more conservative in terms of using ACC and some people are more risky? So we actually set up a questionnaire to complement this study, and the questionnaire included like different types of trust questions as well as different types of driving styles. So there are 12 questions associated with trust and 15 questions associated with driving style. So just to give you an example of some of the questions that we asked them for trust, like things like, what is your overall trust in ACC? What were your trust in like the information that was displayed on the screen? How likely are you to trust the cooperation between ACC and what goes on outside? In terms of driving style, just to kind of get a profile of what these drivers are, we looked at whether or not they tend to drive really fast, whether they plan trips in advance, or whether they actually tend to ignore distractions not from themselves, but also from others as well. So we looked at this in the context going back to the cluster analysis, and we looked at the conservative groups, the moderately risky and risky, and what we found out was that those who were in the risky group tend to actually be very easily distracted. They were not only easily distracted, they trust ACC for everything. Going back to those 3 questions, this group actually said, yes, ACC will do this, ACC will do that. They thought ACC will do everything. So that was very interesting, whereas the conservative groups, they had a high level of ACC trust, but they didn't trust that it would do it for everything. So it was high in terms of like, what they ranked it at, but they didn't just say that, everything was like 5. And then the moderately risky, they felt, very confident in their own driving skills, and they tend to drive a little bit faster, which is why they're not super conservative, but they did have some slight riskiness in behavior. But of course, just like with naturalistic data, there are challenges associated with simulator data as well. It's not the real world, and you cannot really control for everything. And I don't know how many of you have ever been in a driving simulator. So do you get sick? No, sometimes. So those that can actually go through a driving simulator study, that's pretty good, but there's a sampling bias associated with that, because some people just actually cannot go through a whole entire study. So when we design these studies, we're actually very careful, like how long we actually have them in for, and we also do a whole simulator screening about them. Even though we do all that, there are still some people that will, hurl. It's pretty bad. But so there are different types of biases associated with it that we have to take into account. I mean, how many of you have ever done like a, one of those like motion simulators in Disneyland or Universal Studio? Yeah, what do you think? Fun, but like, do you get sick? Oh, do you feel sick? No? No, you guys are great. Just wait till you get older. So, but there's also, the other thing about simulator studies is that there are just certain things that you can't actually have repeated measures for. Like, so once I have a person like maybe encounter a crash or a hazardous, or some sort of a hazard, it's going to be very difficult for them to actually encounter that situation again, because their behavior starts to change. Like if you think about those of us who've ever been involved in a crash, your behavior immediately after that situation changes, at least for a little bit, and you're a lot more cautious. You drive a little bit differently. So there are certain things that we can't actually look at in terms of repeated measures, because there is a learning effect associated with it. But going back to this graph, one thing that I guess I'm trying to advocate is that when we're looking at trying to understand what the driver does and what types of systems that we should design, we cannot look at just like one type of data. We can't just look at crash data. We cannot just look at survey data or just naturalistic or even simulated data. Now we actually need all of these things in combination to get a better picture of what that driver does. We need to understand what their actual risks are, what their perceived risks are, and how they're going to respond, and then how they would be responding to the next situation and the next situation, and whether or not they would actually respond similarly if they were to encounter different things. And so you need a combination of all these things to be able to get what that complete picture is. So, when we think about the differences between naturalistic and simulator data, naturalistic is great for looking at observing varying traffic conditions and seeing things that we may not have ever noticed before. And what's nice about a simulator is that I can take those conditions that I saw that I never realized and design it so that I can have it repeated over and over again among multiple participants or multiple drivers, not just across one person. The other nice thing about looking at both of these from the different spectrums, the naturalistic and the simulator, is that both can actually be complemented with other types of data. So oftentimes when I'm doing this type of studies, I'm looking at it in the context of video data, eye tracking data. I also collect information on EEG. We're actually doing a study right now at the University of Washington looking at older drivers, and we're actually doing fMRIs on them as well so that we can get kind of a different picture in terms of like their cognitive functions. And all of these things, though, actually encompass multiple observations. Typically, if I'm bringing somebody in to do a study, I don't want to collect just one data point. I want to collect multiple data points. So you have to make sure that you take that into account. As a matter of fact, repeated measures is very important to understand in terms of how we control for things or examine things statistically. And the observations, if they're on the same unit, they can actually be very, very highly correlated, and they contain some common contribution that you have to account for. And not only that, but depending on how long you're collecting data, whether it's over a day, over a month, over a year, that variation can change over time, and that also has to be accounted for. So the variability and the correlation contribute to, what's called the covariance structure for those of you who've taken probability and statistics, and trying to be able to figure out how to look at that. And there's also different types of repeated measures. When we look at participants over different types of conditions, that's different from looking at it over a sequence of time, which is different from just doing a before and after comparison. So, oftentimes when I talk to people about how they do their studies, and as Panos mentioned, as an associate editor for a journal, I see a lot of papers, they do a lot of t-tests, and they just like, this is my comparison, but they don't take into account what these repeated measures are. And it's very, very important. So if I look at just for example, this graph, if I just look at A and B, I say, well, it looks like that A is positively correlated with B, right? Or is it? Now, what if I told you that this was actually taken from 3 participants? If I tell you it's taken from 3 participants, and this is what their combination of data is, you can see that that positive correlation is not really so positively correlated. And so this is what the covariance structure does, is to take that into account when you're actually doing this type of examination. The other project that we're doing that also relates to looking at repeated measures is we're doing a lot of stuff with the driver distraction, looking at how often they look at text, whether they're looking at entering text, like typing in text, like texting, or reading a big series of text. So what we see from this diagram is that we see that entering text on your cell phone is actually takes your eyes off the road a lot longer than even just reading something up to 130 characters. And what's interesting is that in the literature, it actually shows that if your eyes are off the road for more than 2 seconds, your crash risk actually goes up. But what's really interesting about this is that when I look at this is a culmination of many different participants. And when I look at each of the individual spread of the data, you can also see for the text entry that this variation is very different from this. So we have the repeated measures effect, which is like this. Each one of these lines is a participant. So you can see if their eyes are off the road for quite a bit of time, even with 4 characters, it's probably going to be off the road for a longer time compared to somebody who's like in a different line. So that has to be taken into account. It's just not only the spread in the data, but also like, how much repeated measures there are. So when we look at these 2 graphs, we have to account for these differences also when we're doing things statistically. So in conclusion, I guess I just want to say that when we look at technology, there's a lot of advances that we want to look at, and we want to recognize that, or we should recognize that there's a lot of safety issues associated with it, because a human being can just do so much in a car, and we keep adding all these technologies, and we have to figure out how best to integrate it so that we can actually perhaps use technology to help mitigate the effects of technology. And to do that, we have to be able to look at all these different complementary data sources, whether it's naturalistic driving, a simulator, survey, or crash data, or video data, and try to figure out how all of these things kind of relate together. So data-driven outcomes, in my opinion, is very important. And we have to be able to use all of them to not just look at the associations, but also the causality. And trying to understand, if we can get that picture, then we can understand how to validate what that driver framework is, as well as the driver model. So understanding what that relationship is, the triangulation of all these different data sources is incredibly important. And so with that, I just want to thank you for your time. I just want to tell you that the work that I just talked about, I kind of talked a little bit fast, so I apologize, but it's funded by the National Science Foundation, the National Academies, as well as the USDOT, NHTSA. There's 2 graduate students' work that I presented. And we're doing a truck study, so that's me in the truck. And if you have any questions, I'm here to answer them. Yes?
Can you go back to the slides that talked about the, I guess, the effect of ACC?
Yeah, which
the
one?
Conflict and the risk. I don't remember which slide, but any of
Okay,
those
tell me when to
slides.
stop.
The one that was curves about I guess reaction time. Yeah, you go back further. Go back furthermore. Yeah, right here. Yeah,
Okay.
right around here. Can you explain this a little bit?
Yeah, sure. So in this graph, so I apologize for going fast, so I'll go a lot slower, which is, so this basically tells you the green line is the car that the subject is in. The green line. The red line is the car that you're following. It's the lead vehicle.
Right.
And so what happens is, so there's, can I go back one more slide?
Yeah.
So in this one more, so there are different parts where the ACC system is trying to figure out when to give you a warning, right? That we're gonna slow your car down.
Right.
So the ACC system, what it does is it will always tell you when it's gonna slow you down. So you have the opportunity to slow down first.
Oh, okay.
Yeah. So in this situation, there's, like if you're in the low risk area, it's gonna do nothing. Once it gets into a conflict, it will actually start giving a warning. And then sometimes, like for drivers, it actually may not come, quick enough. So if you notice in both the conflict and the near crash event, the ACC actually comes at the same time. It actually, like if you look at the time, it actually will trigger at about the same time when it sees that the differences between you and the lead vehicle is about a certain distance that's close, okay? But what happens is, in the conflict event, you may actually see that the car is much further away, so you can intervene a lot quicker. Once you intervene, then the system no longer collects information because the conflict, it's over. Whereas this one, it continues on. So it takes longer for the driver to actually respond in this situation. Does that make sense?
Still not very clear, sorry. So in a near crash situation, ACC also gives a warning.
Right
like
here.
Yeah, right there.
Right.
And then the driver will not respond?
The driver will respond over here.
As soon as the other, why? Why the driver
These are
doesn't-
two different situations.
Uh-huh.
So the reason, I don't know the reason why, actually. That's a good question. I don't know the reason why, but basically that's when he responds. He or she responds.
Huh.
Yeah, so basically all I'm doing, by the way, this is such a good point that you're bringing up. Because
That's
with
a
natural,
causality issue.
Huh?
I mean, because, am I understanding correctly?
Yeah.
Because the driver doesn't respond, therefore you have this near crash situation.
no.
It's not that?
Okay. So all I'm doing
I didn't quite
naturally is,
understand
no,
this.
that's okay. What's your name?
Jermaine.
Jermaine?
I'll talk to you after.
No, but let's talk about this just a little bit.
Yeah.
Which is, in naturalistic data, all I'm doing is observing the situation.
Yes, I
I
understand.
can't tell you why they're doing it, I can tell you what I see,
Mhm.
right?
Sure.
So, go back to this graph. So
Right.
in this graph, this is the trajectory of one person. This is the trajectory of another person,
Oh,
okay?
good.
So in both these situations, once you hit the conflict, ACC will say, I'm going to slow down. And then it's up to the driver to basically do something.
Right.
So you could actually be hovering over the near situation. The ACC is going to start like here, but you might actually have been in a very dangerous situation to begin with.
Uh-huh.
So in other words, you're hoping, so for some drivers, they're hoping the ACC is just going to immediately slow down. But sometimes it doesn't.
Uh-huh.
So it takes them longer to actually respond,
Oh, okay.
right? Scary, right? So what happens is, over here, so what this data is collecting is basically the difference between the range and the range rates, based on the radar system that basically is collecting information. So over here, in this situation, so ACC just kicks in at the same time when they see that the distance is about the right. And then in this one, the driver was able to just respond really quick. And in this, and in this part, they don't, because they just were hoping that ACC was just gonna slow it down.
So,
Yeah.
so what is the programmed behavior of the ACC? How long does it wait before it slows the car down?
That is such a good question. So, this system was actually done by a car manufacturer. So I'm gonna tell you right now, we actually backward engineered it.
Oh, they wouldn't tell you?
Huh?
The Toyota wouldn't tell you?
This
The
wasn't
algorithm?
Toyota, this was another American
whatever.
car manufacturer that's located in Michigan.
Okay.
But, yeah, they basically, we had to reverse engineer it actually to try to figure out what the system was. And the reason why we reverse engineered it was because we were trying to figure out exactly how it was calculating out. So it doesn't calculate it based on just 2 seconds or 3 seconds. It's based on what that range rate is. So even though it kicks on this, I'm gonna slow down ACC. Once the lead vehicle is further away, it no longer slows down. So it's it hesitates a little bit because that car might actually move forward ahead. But it might move closer, which is what happens. Scary. So that's why when we were looking at the distributions of all of these different events, of when this situation becomes conflict or near crash, we were trying to see how often that the driver would actually intervene. So you can see in this situation, ACC for a near crash, it takes them longer to intervene. It's hard. It's harder for them to slow down. It's very, yeah. It was kind of scary. Yeah.
Can you go back to
Sure.
So does the initial speed counter-estimate response to different situations in this case?
Can you say that one more time?
Does the initial speed, like the speed when ACC?
So the initial speed is the speed that you set it at. So you set it at whatever the speed is.
Okay, because I feel like those two figures don't have the same speed.
They're different people.
Okay.
They're different people, so they set it at different.
It's a single case for two different people.
These are different people these are two different cases, two different people.
Okay.
Right, so this is just one person that basically set it at whatever, and this is another person. The point is that ACC always kicks in at a certain time period. So it's based on, so what ACC does is it does it based on the range and range rate. And so you can actually set the distance that you want. You can set it at very close, closer, or closest. And it's based on that and how fast you're going. So you can actually, set it at, however, 100 miles per hour if you want.
So could we set up the ACC based on time to collision rather than the distance? Like the
You know what?
the time
That's exactly what they should be doing. But this particular algorithm was not based on time to collision. It wasn't, yeah.
So have you looked at different ways to display what the ACC is doing to people to see if that affects their behavior? Similar, because,
Yeah.
I did some analysis years ago now with Amy Pritchett about parallel approaches to runways, so aviation, and looking at different ways to display the algorithms of how the collision detection system was working, and we looked at issues of trust, and we did some decision modeling. So is that something you've been doing, or?
So we didn't do that with part of this study. Actually, John Lee actually did a bunch of that, like when we were all in Iowa looking at different ways to set up the displays.
Okay.
And how often should we have a looming effect, or whether we have different levels of colors as well.
Mhm.
So they do actually have all these different types of they have done a lot of studies on that to look at what would work best. What we did in this study was basically look at what was actually out there, and then given what was actually out there, how they would actually use it. Now, one thing I want to mention is that the reason why we use the Toyota Lexus system, which by the way is very different from the BMW, which is very, very different from another system. The reason why we use the Toyota Lexus is because we wanted to bring in people who have already used ACC for some period of time into our simulator. And in the state of Iowa, trying to get even 25 people was really a challenge, because these were people that had to have used the system for a long period of time, lived somewhere in the area that they're willing to come in to pay $20 to $25 an hour to do our study, and it's only for a couple of hours. And so it was, so there is that, so going back to sampling bias, that's also another sampling bias. So, yeah. So we actually did a similar study in Washington State where we brought in some additional people. And then what we also did was we wanted to bring in people who have had the system but have never used it. We couldn't find people who claimed that they have never used it. So, but I'm just gonna sidetrack just really quickly. Remember I told you that the mean age was about 56, because most people who actually have these systems and use it are most likely older. We had a 22-year-old come in and said that he's been using it for quite some time. We're like, really? Huh? So we had him come in, brought him in study, and we're like watching him going, he's never used this before. And so we found that it was his parents' car. And he was trying to like make some money, blah, blah, blah. So we do have, so there's a lot of, when you're doing these types of experiments, you have to take into account all these things and that there could be some biases, there could be some, misleading data.
And so between the simulator data and the field study data, did you see, so in the simulator you classified people according to their riskiness, and I think those two people, right, the one on the right is risky and the one on the left is more conservative.
Correct.
Did you try to look at the data in similar ways across those studies?
So I have a student that's actually looking at this right now. So I'm just going to jump all the way to the cluster groups. So in this group, so basically we looked at these measures, and then we're trying to like backtrack to look at like the measures that comes from the field data. But I want to kind of clarify a couple of things. So this data comes from Toyota. The other one comes from a GM's. So whatever. From Michigan. From a different system. So their algorithm was set up a little bit differently. So, but I want to go back to this young lady's question, which was a very good one, which is, did they use time to collision? Because when we back engineered it, we found that they did not use time to collision. And the reason why is because designing a system with that algorithm is a lot more complicated than what they're actually doing. Yeah. Yes.
Just about the device sensor, the reason that it doesn't work for stopping both condition, is it because of the sensor capability?
Basically, the algorithm is designed to look at two moving objects. So I'm gonna again backtrack a little bit. So when they first started this, because I also used to work for the U.S. Department of Transportation, the Volpe Center, and I was part of the independent evaluator to look at some of these systems. So when they actually had it designed to trigger off just anything that was in front of them, there was so many false alarms. I mean, it would trigger, like if you're going around a turn and you pass by a light pole, it would just go off. So they actually had to redesign the algorithm so that it would not just be based on anything that's just around them, the furniture around them. So it's definitely not perfect, and there's still a lot of issues associated with the automation. But this was their attempt to try to not just detect anything that was just standing around. The problem is if there's a deer in front, like in Buffalo there's a lot of deer, and it's just standing there, it's not going to detect it. So really, make sure that you're vigilant and see what's going on. The reason why I started this study was because one of the things I noticed when I was doing that independent evaluation was that a lot of people were starting to, first was really nervous about using it, so they didn't trust the system very much, but then once they did, they started over-trusting it and thinking it was going to stop in every single situation. So there was a negative and opposite situation, is that the system was supposed to be designed like, people were like, yeah, it's pretty cool, it's pretty safe, but it wasn't really safe if you're no longer vigilant about what goes on. Yeah.
Can you describe a little bit more about the simulator that you had at Iowa State? I mean, what
This
about
is
the
University of
background?
Iowa.
Oh, University of Iowa,
Yeah.
right. What are the sort of background traffic that you can have?
You can have, yeah, that's a good question. So, I'm sorry, did you want to say something more?
Yeah. How realistic those background traffic is? I mean,
So it could be any level of congestion that you want. So basically, in most studies that we do, we just have very light traffic. Light traffic means that there may be like a car or two, like if you're going this way, that there's a couple of cars oncoming.
How did you generate those traffic background?
In terms of like, what do you mean? Like, how do I generate it? Like it's part of the algorithm, and you can actually design how often that they come. Is that what you're asking?
I mean, how realistic are they? I mean, I know some of the traffic simulators, they have the kind of built-in everything all in one package type of thing. You can select, here are the traffic. But as far as, how realistic they are, I mean, it's certainly questionable, because there are better standalone traffic simulator that can generate, you know, more realistic traffic based on microscopic traffic models, as you probably know, right?
Yeah.
So
like
I'm
this
just
thing or
asking what
something.
kind of
Yeah, so
traffic?
it seems pretty realistic to me. I mean, how realistic, but, so what they do is they try to figure out, so we try to design the studies based on whatever the level of traffic that we want to look at. It could be, if we're looking at like intersections or like urban areas, we design a different traffic scenario. So it looks very realistic to me, so maybe I'm not answering your question.
Visually
Visually it looks
realistic,
fine.
yes, yes.
Visually it looks like
I'm
there's
talking about the volumes, the speed,
Right.
and the behaviors of
Right.
other vehicles in the background.
Right, I mean, it looks realistic to me, and we actually do a lot of work with, so there's like different groups of people that design it. So we have like computer science, electrical engineering people that help design the algorithms. We have civil engineers that help us kind of adhere to certain guidelines in terms of even the vertical and horizontal geometry. Then we have people from like the industrial engineering side that helps us look at like the experimental designs and like what we should be like controlling for. So there's different groups of people that actually, at the University of Iowa, that kind of work together.
I see.
So I'm actually now at the University of Washington. So I actually have this exact same software in my lab, but I don't have a motion-based simulator. I have a fixed-based simulator, but it seems pretty good. I mean, I think it looks really good. I don't know in terms of like how they actually designed the algorithm, quite frankly.
We'll
But
probably talk more about it.
yeah,
Very
I'm happy to do that. Yeah.
Right. A follow-up question is, you know, I mean, you also talk about limitations of driving simulator-based study.
Yeah.
You know, you still cannot control
That's correct.
everything. You
That's
know,
correct.
especially when it comes to,
That's correct.
I suppose, you know, new technologies that are not even there. I mean, there's many
Well-
what-if situations.
Well, we can't control for them, but what's nice about driving simulator study is that we can test for them before a car manufacturer tries to spend millions of
Sure,
dollars to
sure,
implement
exactly.
it.
Right.
So we can actually, like, many car companies actually do a lot of the testings in these simulators to try to look at what the differences are and whether or not this would work better for older individuals, for, you know, more at-risk individuals. So they do look at those different types of scenarios.
Mhm.
So that's the value of a driving simulator.
Sure.
But I absolutely agree, we cannot control for everything, which is why it's not all the way out of the, you know, left end of my chart. So it's in a little bit more because it's not quite, but it's definitely not
Right.
fully realistic. But for a lot of people, it gives them the opportunity to have the participant in a driving environment where they're actually using the steering wheel instead of a joystick, for example.
right.
So that we can see whether or not lane positioning would be appropriate.
Sure, sure. Well, my last question is, you know, if you have sort of, you know, lots of money, billions of dollars,
Yeah.
what would be sort of your on your top of your wish list in terms of a experimental test bed environment?
Well, I don't know, I guess I've never thought, I'm
What kind of
actually-
what
yeah.
kind of experiment do you want to do? Like, where, you know, if you have lots of money to.
Well, I don't know, I'm not really sure how to answer that question, but I'm actually very happy with like what I'm doing right now. Like, I really am. Like, what did Pamela say, how much do I have? 19 million apparently. So, I actually get to
$1
do,
billion.
what was that?
What if you had
What do you
$1
have, $1 billion, yeah. I mean, I really enjoy looking at these different types of behavior, and I think the one thing I guess I would say is, it's not the sophistication of the tools, but it's what type of data I can collect, and how many participants I can get. I'm actually limited in terms of like how many, like lots of times the resources is not based on the equipment because I already have the equipment, and sometimes I need to supplement it with like things like fMRIs, EEGs, or eye tracking, etc. But it's trying to get the right participants, a more unbiased sample to come in so that I can actually get some more true indicators of things. So, I mean, I'm doing research right now, like I'm going to Washington DC after this because I'm giving a talk to NITSA about the auditory distractions that we're doing. We actually designed several voice control systems, and we've also like helped with the visual manual guidelines that they're working on. I'm doing work with Toyota, I'm looking at, I'm being videotaped, pedal misapplication, you know, issues. So I'm looking at quantifications of that, and that's basically a simulator and a naturalistic aspect as well. I'm actually working on a large truck study with Federal Motor Carrier Safety Administration, where, you know, this the 3,000 vehicles that they're shrinking passenger cars, we're doing the same to trucks. And we actually have 500, drivers, across the U.S. that we're collecting information on. And we're trying to figure out whether or not providing feedback to them would be a good thing, and can we help modulate their behavior in a good way based on that. So I actually love the work I do. I mean, I don't know. If I had $1 billion, I'd be doing the same thing.
Okay,
But
great.
in Buffalo,
Okay.
in Buffalo.
Thank you very much.
Yeah.
I have to go, but I hope I can come back before 3, around 3 to talk
Yeah.
to you. You'll be available till 3:30, right?
Yeah, and you know what? I don't know if you saw, but I'm on Twitter.
We've been getting 133. We've been getting 133.
Yeah, I'll come back. I have a meeting from 2
Yeah,
to
but
3.
see, like, you can get a hold of me, like, here's my email, my Twitter account, and my
Excellent.
web. I figured out how to use Twitter, I'm really excited.
Thank you.
Yeah, thank you. Yeah,
So it seems that the Google car,
yeah.
kind of as spooky as it still seems to me, does this very well. And if it's using something like adaptive cruise control all the time, how is it that it's so much better than these systems? Or if it's not, how is it?
Yeah, so when you say
operating
it's so much better in what situation?
Well, without any human input whatsoever, it seems like they can fairly easily navigate without colliding into anything.
Yeah, so let me clarify what I'm saying. So it's very, very good in what situations that you've seen the testing at?
And driving around cones in a parking lot?
Exactly.
Okay.
Thank you. So we're not going out and buying those tomorrow.
It's good.
We can make it.
Yeah.
I'm just curious, I mean, during the experiments using simulator, are they usually allowed to use their cell phones?
So in these, we actually control what they're doing. So we actually tell them, like, so for example, like the driver distraction study I was talking about, we actually have them engaged in the task that we have them do. So they're not using their own cell phones. That being said, you can actually design a study where you may be looking at different types of cell phones that they're using. But in the studies that we do, we actually control the type of distraction that they're working on, because we want to try to see what the changes are. Yeah.
Now that there was a mention of Google self-driving
Yeah.
cars,
Yeah.
do you have any comments on they're testing the vehicles
Yeah, they are.
on
They
the
just-
road,
yeah.
real world
Yeah.
setting?
Yeah.
and
I think that's really cool. I think it's really cool.
Sensors are better because it can handle all types of traffic.
Right, so there's actually an autonomous vehicle group, and actually several students that got PhDs and masters from the University of Iowa are actually working in that group right now. So they are doing some testing to look at, like, what else you can do. But I think that in terms of like having a fully autonomous, transportation network, I think there will be, we're getting closer and closer to an autonomous car, but I truly believe that the human will still be in the loop. I mean, there will still be the occupants, the pedestrians, the bicyclists, and I was just in China, the rickshaws, there's just gonna be a lot of people that do not, and individuals and types of motorized vehicles that do not have these types of sensors. So the ability to connect to all these different things is still some time before that will happen. Yeah.
So for such a system, do you think it would be possible for each car to independently be operating a fully autonomous system, or would there have to be inter-vehicle communication to make it work?
My personal opinion is that there should be some sort of communication. But that brings up a whole bunch of other issues, right?
Mhm.
There's a cybersecurity issue. There's also the legal issue. Like, let's say there was a crash. Who's actually going to be liable? So there's a whole bunch of other issues that comes up with a truly, connected, automated vehicle talking to another automated vehicle, which is talking to, like, what goes on the road and in an intersection. So I mean, that test bed I was showing you, that safety pilot that's going on at the University of Michigan, has 5 car manufacturers, and they're actually doing some really cool stuff, looking at like how the sensors talk to each other. But again, because the human will always be in the loop, trying to understand, what all the issues are associated with that, with humans and machines working side by side, are still going to be, prominent issues for quite some time. But in a good way, provides some interesting challenges.
I mean,
Yes.
as a follow-on to that, you have to think about who drives, okay? I mean,
Yeah.
as opposed to who flies highly automated aircraft.
Yeah.
And whether whether the range of populations that we put in cars are going to be able to manage manage these cars.
That's right,
Y-
yep.
You know, and,
Yeah.
well, I guess I'm on video too, right? So about the stories I've shared in class about relatives who can't turn their TVs on and off effectively, right?
Yes, that's correct.
Everyone is not gonna
That's
be able
correct.
to get in these cars now.
Right, and you know, it's funny, building on that, so a lot of discussions that we have among like the transportation group is, how do we actually buy a vehicle for our grandmother, where she just wants like an AC and, you know, maybe the radio, using a knob. And one of the things that they talk about from a usability study is, you know, this, again, the technology is not going away, but how do we actually integrate the technology such that someone like my grandmother or my mother would want to use it, because it is as easy as trying to just turn on the radio or the AC. And it is a challenge. And it's something we all have an opportunity to kind of maybe, you know, play a part in. I think it's really, I think it's an exciting time, actually. Yeah,
I missed your whole presentation. I had a class
that's
that just
okay.
came.
I can do it in 5 seconds.
I just have a general question. I was wondering, let's see, if you place all these required sensors to a vehicle, so how much the cost will be increased, and how, you know, this increased cost would influence this auto industry. I mean, sometimes it's nice, you know, to add like more and more features.
Right.
The users don't want to pay to purchase these features, and eventually, you know, it's not
So,
economically beneficial to offer them.
So the first part of your question in terms of like how much the technology is, I don't know the answer to that. But the second part of your question about, you know, are users willing to pay for it? They're paying for it now. Oftentimes when we buy a car, we buy a technology package. So going back to my surveys about adaptive cruise control, many people, so the way we sent out those surveys was, each car, you have a VIN, a vehicle identification number. That vehicle identification number not only identifies the make, model, but also what the options are associated with your car. So many of the people that we sent it to didn't even know these features existed, but they bought it anyway because it's part of a technology package. So many people are already buying technology packages, and they don't really know what all the features are that come in with their cars, but it's there.
Can I ask one more?
Of course.
So, for the simulator thing again,
Yes.
can you control the fear of accident for participants?
The
For
field of accidents,
fear of
the fear of accidents.
Yes.
You know,
no.
I don't really know how to control fear, but I can measure fear. Like, I don't know if measuring fear is the right word, but I can look at, like, you know, subjectively, like what their levels of stress is, workload, nervousness, anxiousness, and we actually do that. But like, I can't actually control for it in some respects. What I could do, kind of going back to the cluster analysis, is we can do one part of the study where we group people into different categories. And then from there, kind of, you know, have them come in, like get an equal sample size to do some additional studies. But I don't typically control for fear.
So I'm asking this question because
Yeah.
I'm interested in the hazmat transportation, and I heard that the biggest stress source for hazmat truck drivers is that when an accident happens and they die. Because the hazmat explode or something,
Yeah.
something bad thing
Okay,
happen.
yeah.
So when they do some experiments using the simulator, so that kind of thing
Oh.
must be accompanied,
Oh, okay.
right?
Huh.
So then they will be more conservative in actions.
Yeah, I'm not as familiar with that research. Of course, if you're gonna drive hazardous material, there's probably a level of fear
Yeah,
there
yeah.
to begin with, right? So, yeah. Yeah, did you have
Well,
some?
I was gonna have a follow-up, so it's not exactly the same thing, but in some, the high-fidelity clinical medical simulations, people get really stressed out when they kill the mannequin patients. So the more realistic the simulators are, the responses that people have in them become, I mean, it's never gonna be the same as the
Yeah.
actual fear of a
Yeah,
real accident.
Yeah.
But it's not correct to think that there's no enhanced emotional response
Right.
to those kind of situations,
Right.
because we see it in other pilots
And
don't
we-
want the plane to crash in
Yeah.
in those training simulators.
And that's what I was saying earlier, like when we actually have a hazardous, you know, some sort of hazard, or if a truck comes out, or if a child comes out and they hit it, we actually stop. The experiment is pretty much like, that's the end of the experiment, because we know that their behavior will change afterwards. But in terms of like actually like separating out people into different groups based on fear, I don't typically do that, but we actually do capture what that emotion is. Does that, and what they do, like how their performance is during that scenario. Yeah.
So I'm sort of interested in trust in autonomous systems or semi-autonomous systems.
Yeah.
Do you think there are any like really significant, I guess, pitfalls, or maybe not pitfalls, but like problems with people trusting these systems? Is it that they don't understand it, or is it just that it's not exactly reliable in all situations, or what do you think are the big contributors to not trusting, or like a hesitancy in trust?
So it really, I think there's a lot of things that, I think all of the above in some respects, because there's a little bit of the fact that it doesn't always work in all situations. It's the fact that they could overtrust, and they may actually, and it can actually, there's a huge literature on this that probably Aaron is a lot more familiar with than I am. But there is a lot of things that relate to how you're going to use that system. So what we did was look at how much, so those that are like risky tend to overtrust the system way too much and expect the ACC to take over just immediately. And that's not, that's a negative outcome as well. And then there's those that, they have the system, like going back to what you were saying about you purchased the system as part of a technology package. And you know it's there, so you kind of try it out every so often, but you don't actually trust that it will take over or do the right thing in the right situations. So I don't know if that answers your question, but there's a
spectrum of
there is. And so what we try to do is actually, at least what I do, is try to correlate what those measures are as it relates to trust, and then how that actually impacts their performance when they're using that particular technology. Yeah.
In terms of the road safety related research, is it easier to collect the data or analyze the data?
Wow, it's easier.
Which one?
I'm going to change that around a bit. It's easy to collect lots of data. It's really hard to put the data in the right format for the analysis. The analysis itself is not hard. So my students spent a lot of time reducing the data, segmenting the data into the right format so that you can actually put it into the format for analysis. So data collection easy, analysis not so bad. Getting it into the right format, very, very difficult. It's a big challenge.
So you're also dealing with kind of like big data.
Lots of big data. So big data, let's define what big data is, right? Because big data is not just like a large spreadsheet, but that there's velocity associated, right? Because the data is constantly changing and moving, right, while you're trying to analyze it. So yes, the answer is yes, we are dealing with that. We're dealing with a lot of longitudinal data. It's not just, it's relational, so there's different levels of the data. There's different ways that the data is being collected. Some data is collected at like the person level. Some of it is collected like in the driving simulator at 50 frames per second. And you need to try to figure out like how that 50 frames per second is going to relate back somehow to some higher level. It's a lot of work. And then you throw in video data and like heart rate monitor, which is our heart rate variability. And there's just so much noise, so you have to kind of smooth it out, clean it out. So that's what my students spent a lot of time doing. We have a lot of undergraduate students that help us in the lab with that. So.
Well, perhaps we could take it over to Keter 133 with whomever is interested. So with that,
thank you so
Linda,
much.
thank you so much.
Thank you.